Howdy, howdy, recalculus friends. Today, we're going to talk about ellipses. Today, at the moment, is where are we at? 13, 3 months away. 21. Most of you are taking the ACT or took it, or you're getting ready to take it on Thursday. It's Tuesday, so I missed my A group homies, first and second period. I hope the test went well. I thought I'd make a quick little 20-minute video here to talk about ellipses so that you have something to do when you're sitting home bored. The ellipses, honestly, they've got new vocabulary, there's new flavors, there's new tasks to try, but for the most part, it's a lot like a circle. So you see by my picture here, I'll make this picture go away. The circle was the set of all points equidistant from a point not on the circle called the center. The set of all points equidistant from a point. So if you pick a point in the middle of a circle, that's called the center. And every point from that center is the same distance, right? Every point on the circle is equidistant from the center. Well, an ellipse doesn't have that definition. It's slightly different. But an ellipse is similar to a circle in that it's like somebody sat on it, right? And squished it, made it oblong either horizontally or it could be oblong vertically like this, right? And so my first thought was maybe we talk about the equation of a circle because that's where we were, last week with our definition of a circle. The form was what you see there in blue, x minus h quantity squared, y minus k quantity squared. You add those together and it equals the radius squared. So an example of that would be like x minus 2 quantity squared plus y plus 1 quantity squared equals 4. And just for fun, if you wanted to, what you could do, just for fun, is divide everything by the radius squared. Divide by 4, okay? Divide by 4, divide by 4. And the equation of a circle, it could be written this way. Now, this way is not how we normally do it. This way is a little bit weird because we're using fractions. But you could do that. Those two equations are the same, right? If I erase all these divided bys, those two equations are the same equation. They're both a circle centered at 2, -1. The radius is 2. But what I want you to pay attention to in this second equation is how the denominators are the same. If the denominators are the same, if they are common denominators, what you could do is multiply everything through by that denominator, and you would go back up to here, right? Where you'd have a 1 and a 1 and a 4, right? If you multiply the whole equation through. So an ellipse being different than a circle is kind of interesting in that its formula is very close to a circle. So if I were to take one of those 4s in the denominator, like take this 4 and make it a 9, notice how you don't have a common denominator anymore, right? Notice how if you wanted to multiply through by the common denominator, which would be 36. If you multiply through by 36, you would get 9x minus 2 squared plus 4y plus 1 squared would equal 36. That's multiplying through by the common denominator between 9 and 4. And notice that's not a circle. This equation right here does not match our circle equation, right? Because the denominators are different. So when you denominator differently, that's when you have an ellipse. The different denominators force the circle to become oblong in one way, like horizontally or vertically. And that's what we got to figure out is which way does that happen. Notice when you multiply through by the common denominator, you get a 9 out front or a 4 out front. And those two things indicate that it's not a circle. See, to be a circle, those can't be there. They have to be the same coefficient. Okay, if they were both 4, then I could divide everything through by 4, and I would end up with a circle, right? But when they're different, You can't get rid of both of them. Okay. Now, how would you get rid of them? Well, you could divide them both by 36. And if you did that, you'd go back to here. You would get this equation equal to 1. See how it equals 1? Boom, this one. And that right there, my friends, is the equation of an ellipse. Our equations today are going to look like that, okay? So now, what is an ellipse? Well, take the circle, okay? Go back to the circle and look at it. And imagine the center of the circle were to go through some mitosis, right? I think that's what it's called. Cell division. And imagine if the center of the circle split into 2 foci. Sometimes I say foci, sometimes I say foci. What's the difference? I don't know. I don't even know if it matters. But if you have 2 focuses, we don't say 2 focuses, but we say focus point and another focus point. If there are 2 foci, the definition of an ellipse is the set of all points, the sum of whose distances from the 2 fixed points called the foci is constant. So remember a circle. A circle had a center. Imagine if the center of the circle split off into 2 foci. What would then happen is you'd almost have like 2 radii, but they're not the same. So D1 and D2 do not have to be the same length. D1 and D2 are the distances from each focus to the point on the ellipse. Those 2 distances have the same sum. D1 plus D2 is constant for every point on the ellipse. So if I were to pick, not this blue point right here, but pick a red point, like right there, this distance plus this distance would be the same as D1 plus D2. Okay. Pick a different point, like this one right here, on the very, very like left edge of the ellipse. This distance from here to here plus the distance from here to here, from focus to point and from focus to point. When you add those 2 numbers together, they would add up to the same constant. So the definition of an ellipse, the set of all points in a plane, the sum of whose distances from 2 fixed points is constant. Okay. It's different than a circle, but it's similar to a circle. See, with a circle, there's only one radius because there's only one center. And every radius is constant. Every radius by itself is constant. But for an ellipse, the constant comes from adding the 2, they're not radii, but they're like radiuses. From the foci to the point on the circle, you get 2 distances. So those 2 distances added together is always the same constant. Now, what's also slightly quirky is if you look to the right, an ellipse also has a center. Okay, so when it comes to the center of an ellipse, it's still going to be the HK. The center of the ellipse is HK, just like it was for a circle. Okay, somewhere in line with the center, there are the foci. Okay, now you see with an ellipse, it could be orientated so that it's oblong horizontally, or it could be oblong vertically. So what happens is we have 2 different axes. There is a major axis, which is the longer of the 2, right? The minor axis is the shorter of the 2. And you've heard of like majors and minors, like in college. Like a major is like when you do more hours to get a degree for something. A minor is when you do less hours to get that degree. Okay. So you get a major in, say, like math and a minor in history. You take like 30 hours in math, but you only take like 18 hours in history. And you got differences. In music, there's major chords, there's minor chords. So the major chords are bigger chords. Okay. The minor chords are not. Major, minor, common sense, right? So how do I know if my ellipse has a horizontal major axis or a vertical major axis? That's what we get from the equation, okay? So there is an equation for an ellipse, and there's words here. As a matter of fact, so remember that picture right there of the ellipse on the left. I forgot I had pasted this one down below. So imagine if you tied a string to 2 nails and nailed those 2 nails a certain distance apart. Then you took a pencil and pulled the string tight and traced around the nails with the string, the top half and the bottom half. You'd get an ellipse. And you think about it, the length of your string is constant, right? You're not using different strings. You're using one string. So you take a string, whether the string is 10 inches long or 30 inches long, and tack it down on both ends. You would get an ellipse, okay? If you make your tacks vertical instead of horizontal, then your ellipse is more vertical. So you'll notice a bunch of H's and K's and all that here in the equation. Let's it's bell's ringing. That means the B lunch students are leaving the cafeteria. This video's got to be over in 10 minutes because I'm going to go to C lunch at 12:41. Okay. Here's your equation of an ellipse. Maybe I should just go to here for now. It should look like I was talking about the very beginning of this video. See how there is an x minus h quantity squared plus y minus k quantity squared. That looks like a circle. But notice that it equals 1. And it's set equal to 1 on purpose, okay? The equation has to be set equal to 1 because the numbers in the denominator, the a squared and the b squared, affect your ellipse, okay? How does this work? How it works is a is always bigger than b. A is always bigger than b. Therefore, a squared is always bigger than b squared. What's another way to say that? B is less than a. So if you look at the definition at the top, I'm using a yellow highlighter. Obviously, a and b both have to be bigger than 0. We wouldn't have an ellipse at all if one of them was negative. That's a problem. So b is less than a, which is the same thing as saying a is bigger than b. So notice when the major axis is horizontal, look at where the a is. Look at the letter A in the equation on the left. Notice how the letter A is underneath the x variable. And the x variable is the horizontal axis, right? So if A is bigger than B and A is with the x variable, then the ellipse is horizontal. Look at the second rule. Notice here, the major axis is vertical. The longer axis is vertical, and notice A is with y. Okay, so this is the first decision you have to make with each equation is you look at the equation and you go, okay, which number's bigger, 4 or 9? And then you go, oh, well, obviously 9 is bigger. Oh, well, 9 is with the y variable, so I'm using this case down here where the major axis is vertical. Okay, so undo, undo, undo. I'm going to undo all these highlights. There's some other information here about like the length of the major axis is 2a, the length of the minor axis is 2b. Then what do you know about the foci? The foci, again, the center of the ellipse is HK. I wrote that earlier and said that earlier. Center comes from HK, just like it did for a circle. But then we're going to go from the circle A and B units in horizontal and vertical directions, depending on which way it goes. The foci, ooh, boom. That bell means that everyone's supposed to be back into class, which means I have 7 minutes until C lunch starts. So I have 7 minutes to do 2 examples. I got to start talking faster. How do I get the foci? The foci come from a squared minus b squared. And the foci are the square root of that units away from the center. The foci are c units from the center. And c is the square root of a squared minus b squared. So that should seem a little bit weird, right? A squared minus b squared is like the Pythagorean theorem, except not at all. It's the, it's the opposite of Pythagorean theorem in a way. So you can see it here. Remember, if A is bigger, A is always bigger than B. If A is with X, then the major axis is horizontal and the ellipse is like, long ways horizontally. If the A number is with Y, like it is in the second graph, the major axis becomes vertical. Okay, so then the ellipse is elongated up and down. So let's look, I got 2 examples. See if we can rip through these 2 examples. What do they ask you to do in each of these examples? They ask you for the center, the foci, the Oh, and then the vertices. Did it mention the vertices? I don't think it mentioned vertices up here. Maybe it did. I didn't say vertices. The vertices are the end points of the, they were up here. The vertices are the end points of the major axis. So how do you get the vertices? They are the end points of the major axis. So the vertices are a units away from the center. So let's just get to some numbers. Here is our first ellipse. Notice the denominators of x squared and y squared are different numbers. What you have to figure out first, because a is always bigger than b, is which number is a. Is 9 bigger than 4, or is 4 bigger than 9? Well, 9 is bigger than 4. That means that 9, we should do that over here. 9 is a squared. Notice I gave you a perfect square like 9, and I gave you a perfect square like 4. You're welcome. That was nice of me. So what is the square root of 9? The square root of 9 is 3. What is the square root of 4? The square root of 4 is 2. So my a value is 3, my b value is 2. What is the center of this ellipse? The center, remember, comes from h and k. And there is no hk. So what's the center of the ellipse? The center is 0, 0. Okay? So when I go to make my graph, first of all, is the major axis horizontal or vertical? The major axis is horizontal because the bigger number is with x. Okay? The center is 0, 0. So here's my center, 0, 0. What I do now from the center is I go a units to the right, and I go a units to the left, and those are my vertices. The vertices are the end points of the major axis. So my vertices are negative 3, 0 and positive 3, 0. The major axis is the length between the vertices, which will always be 2a. The major axis is always 1, 2, 3. I didn't like that. 2 times a, which in this case is 2 times 3, which is 6. That's the length of the major axis. The length of the major axis is 6. Now, what about my minor axis? My minor axis is b units from the center. So if I go up 2, and if I go down 2, the minor axis, okay, of the ellipse is 4. The length of minor axis, man, it's going to be tough to go to lunch in 3 minutes, is 2 times b, which is 2 times 2, which in this case is 4. So if you're ever asked for the length of the major, the length of the minor, there you go. Now, how do we graph our ellipse? We just connect those 4 dots, and red and blue make purple, right? So notice this ellipse is oblong horizontally, and that's basically it, except I can find the foci. How do I get the foci? To get the foci, we'll use orange. Remember, the foci are c units from the center, where c is the square root of a squared minus b squared. You take the bigger number, which is 9, minus the smaller number, which is 4, and we get the square root of 5. The foci are c units from the center. So in this case, c is not a super nice number. The square root of 5 is irrational. But in order to make a and b both perfect squares, sometimes c does not work out to be a whole number. You have to really work with your a's and b's. Like if I had made a 36 and made b 64, then no, that wouldn't work because I was adding them. Who cares? Just move on. So where are my foci? My foci are c units. So the square root of 5, in case you forgot, is like 2 point something. What is it? I got a calculator right here. 2.2. So 2.2 is, right about there. This is my C. So what are the coordinates of the foci here? Well, One of them is negative radical 5 comma 0. The other one is positive radical 5 comma 0. And those are all the parts of an ellipse. I almost got both problems done in time. I'll just rip through the next one real fast, right? Center, vertices, length of the major axis, length of the minor axis, the foci, and then the graph of the ellipse. See how it all kind of came together at one time. So my second problem, very similar, except I figured I changed a few things. Notice what's different now is the center. What is the center of this ellipse? The center is HK. What number is H? That's 1. What number is K? That's 2. So my center, there's the bell, is going to be 1 to the right, 2 up. There's my center. I'll make it green. I'm going to finish this problem and then go to lunch. Okay. Which number is bigger? Is 16 or is 4 bigger? Which one's bigger? Well, 16 is bigger, which means that 16 is which variable? A squared or B squared? Well, 16 is bigger, so it's A squared. And notice 16 goes with Y, which means that this ellipse is going to be like vertically positioned. The major axis will be vertical. A is 4. Okay, so if A is 4, what I would do now is go up from the center, 1, 2, 3, 4. So that's one of my vertices. That's one of my vertices. The center, remember, is 1, 2. So what's that vertex right there? Well, it's 1, comma, what is 2 plus 4? 6. Where's my other vertex? The other vertex is down 4 from the center. So if I go back to red, 1, 2, 3, 4, down here, this is my other vertex. Notice the x-coordinate's still the same. I don't change the x-coordinate, but I do 2 minus 4, the y-coordinate. The length of the major axis is now 8, right? So the vertices are 1, 6, and 1, negative 2, right? What's the length of major axis? That will be 2 times A, which is 2 times 4, which is 8. Now, since 4 is smaller than 16, that means that 4 is B squared, right? Which means B is 2. That's really messy. I'm going to try that again. I'm rushing because it's lunch. I hear all my friends going to lunch. B squared is 4, B is 2. So I go 1, 2 units to the left. I go 1, 2 units to the right. So the end points of the minor axis, those blue dots, they don't have names. They're not called vertices, okay? Because it's like the minor axis. We don't really care. It's kind of sad, but that's life, right? What's the length of the minor axis? The length of the minor axis is still 2b, or not 2b. No, it is 2b, which is 4. So how do I graph my ellipse? You connect those 4 dots as best you can. And what's true about every point on this ellipse? What's true about every purple dot? Okay, every purple dot on the ellipse, which is made up of infinity purple dots, is the sum between the two foci is the same. So where are the foci? The foci, remember, were orange. So to get the foci, you have to do c squared equals a squared minus b squared, which is 12, which tells me that c is the square root of 12. And the square root of 12, everybody knows, is 2 radical 3. So what do I do from the center now? I'm going to go up 2 radical 3. And what is 2 radical 3? It's like 3 point something. The square root of 12, in case you're wondering, 3.46. I almost guessed 3.5. So if I go up from the point 1 comma 2, if I go up 3.46, right? I go up 1, 2, 3.46. That puts my focus like right there. Obviously, it's better if I do this on a graph paper, but that's one of my foci. What is the equation of that point? Well, the x-coordinate's still 1. What's the y-coordinate? The y-coordinate is 2 plus 2 radical 3. That's how you'd want to write it. You want to write it in exact form, okay? 1, 2, 3. 16 minus 4 is 12, right? Almost seems bigger than I thought it was going to be, but that's okay. So notice this foci is 1 comma 2 minus 2 radical 3. Those are the foci. 1 comma 2 plus 2 radical 3 and 1 comma 2 minus 2 radical 3. And if you go from the foci to any point on the ellipse, the sum of those two pink lines is the same, okay? If I were to do like this blue, if I were to go from here to here, right? The sum of those two blue lines is the same as the sum of the two pink lines. That's the definition of ellipse. An ellipse is the set of all points whose sum of the distances to two foci is constant. Now, there's something else about foci that I should mention. The foci are what makes a circle less circular. So how elliptical is an ellipse? There's a measure for that. This is in the book. This is called the eccentricity of an ellipse. The eccentricity of an ellipse is how elliptical the ellipse is. And there's a way to get that. It's right here. It's C divided by A. The eccentricity of the ellipse is C divided by A. So note that the circle's at the bottom. Notice the one on the left, that looks like a circle, but that's actually an ellipse. Because the C value, the foci are very close to the center, right? If you move the foci further away from the center, the C number gets bigger, okay? As the C value gets closer and closer and closer to A, the ellipse gets more oblong, right? And as it says up here at the top, one of the reasons it was difficult for early astronomers to detect that the orbits of the planets are ellipses is that the foci of the planetary orbits are relatively close to their centers, okay? So to measure the ovalness of an ellipse, we do C divided by A. C divided by A. So it's something they also ask in each of these problems is, what is the eccentricity? Okay, so the eccentricity is C divided by A. For this first one, remember C was the square root of 5. And what is the square root of 5 out of 3? The square root of 5 divided by 3 is 0.745, which is closer to 1 than it is to 0. So the bigger the eccentricity, as eccentricity gets closer to 1, the ellipse is more oblong. If the eccentricity is really small, the ellipse is more circular looking, okay? So as it says down here, eccentricity is a number between 0 and 1. If the eccentricity were 0, if there was no distance between the center and the focus, that would mean the focus is on the center. What would happen there if the eccentricity is exactly 0? I know you're all saying it out loud. That would be a circle, right? What would happen if the foci get closer and closer and closer to the vertex? As C gets closer to A, the ratio gets closer to 1, which would turn the ellipse squattier and squattier and squattier, and narrower and narrower and narrower. And if it were to equal 1, then you'd have a line, right? So the eccentricity is always between 0 and 1. If the eccentricity were 0, you'd have a circle. If the eccentricity were 1, you'd have a line. So I'm kind of rushing through this, but oh well. It's C divided by A. How do you get eccentricity? You do C divided by A. So it's E equals C over A. And for this problem, remember C was 2 radical 3 and A was 4. And what is the square root of 12 divided by 4? Even bigger, 0.866 is the eccentricity on this one. And my graphs are not really great, but notice this one to me looks more oblong than that one. Maybe not actually at all. I wish I had done one where the eccentricity was really small. We could have been able to tell the difference, but you got it. This video only went 9 minutes longer than I wanted it to, so that's cool. I'm going to give you some problems on ellipses now for you to try on your own this week. Okay, have fun. See you later.